Hey y'all, so I'm sorry I'm not going to be able to hold class on Monday. I figured I'd throw out this video and just kind of run through here how to do one more surface area problem. So my last example of surface area is, oops, let's see, I want that one, it's going to work, is to find the area of z equals x squared plus y squared, and then I will also want to be under the plane z equals 9. Okay, so, we always write this on the board, and then we kind of go, all right, so what does it actually look like? So I've actually graphed it in Mathematica here. There it is. It's a parabola, a 3D paraboloid, I guess, and then z equals 9 is a plane that cuts it off. So what we really want here is we want to figure out what the surface area of this dome is. All right, so we want to be below this plane, and I've inverted it, right, because this is z increasing. Z equals 9 is right here. We want to be below this plane. We want to figure out the area of that surface area. Okay, so here's how we go about that. The surface area was the double integral of the length of r of u cross r of v dA. So this was the area of the surface. Sorry, I'm not very good with this board. So let's try to write out r of u and r of v. The plane is what's cutting us off, so this is really our function. So here's how I'm going to write r. I'm just going to write r of x and y. Keep it really simple, because it is x I hat plus y j hat plus x squared plus y squared k hat. So the parameterization here is actually really simple, really straightforward. Remember, any surface area parameterization has to have two variables associated with it. This does. So this is going to give me the surface, x, y, and x squared plus y squared. All right, that's pretty easy. So let's do the r sub x. That's going to be 1, 0, and 2x. Be careful with your derivatives. My r sub y is going to be really similar. That's going to be the vectors 0, 1, and 2y. All right, great. Let's see if I can figure out how to clear everything. Lasso select. That kind of worked. Sorry guys, I should have practiced, huh? There we go. Okay, so the next thing I need to do is I need to do r sub x cross r sub y. So for me here, that's going to be I, j, k. It's going to be 1, 0, 2x, and 0, 1, 2y. So that vector is going to be I by 0 times 2y, 2 minus 2x, minus j, and that's going to be 2y, and then minus 0. 2y. And then k is 1 times 0. So k is 1. I didn't say that right, but so I get a vector here that's negative 2x, negative 2y, and 1. So that's my vector that's normal to the paraboloid. Okay, now I'm going to need to do the length of that normal vector. So that's going to be 4x squared plus 4y squared plus 1, all under the radical. All right, square each piece, add them all together. So far, so good. All right, so now I'm ready for my surface area. The area of the surface is the double integral of this thing, 4x squared plus 4y squared plus 1 dA. Okay, so now I need to figure out what limits to put here, right? Let's go back and look at our picture for a moment. The limits that we put are going to be where this area sits. This area sits on a circle in the xy plane. It sits on a circle of radius 3. Remember, it's here at x squared, the intersection, the edge. That's really all I'm interested in, the edge. The edge is at x squared plus y squared equals z, which was 9 there. So x squared plus y squared equals 9. And then I want everything inside of there. We've already taken care of the fact that this isn't flat with the argument in the middle, the square root. So all we have to do now is assume it is flat and do the area of that. So the area of that is a, let's put it here, it's a circle of radius 3. Radius 3 because it's equal to 9, r squared. Okay, so, okay, yeah, good. Maybe I'll write something suggestively here before I erase everything. It's a circle of radius 3, and it's the square roots of 1 plus 4 times x squared plus y squared, dA. Alright, so keep that in mind. That's what we're going to do. That's where I'm going to start on the next line here, but let's try to erase successfully this time. Almost. Still didn't get it all. Alright, there we go. Okay, so I want to do the double integral over c of radius 3 of the square root of 1 plus 4 times the quantity x squared plus y squared. Alright, so I want to do the area of the circle. So, of course, I'm going to convert to polar coordinates. Polar coordinates become integral from 0 to 2 pi. They become the radius, 0 to 3, and then inside becomes 1 plus 4 r squared, and then don't forget that you need an r dr d theta. Next, I'm going to do a U-substitution. I'm going to do here u equals 1 plus 4r squared, then du will be 8r dr, so I have the r dr here, so I'll just need to divide by 8, so I get 1/8, 0 to 2 pi. Now the integral goes from r is 0, r is 3, so now we'll do u is 1 and u is, let's see, 9 times 4, 36 plus 1, 37. And then that's the square root of u, du, and a d theta. Feels like forever since I've done a u substitution. Alright, so let's see, I'm going to do the theta integration, that's 2 pi. I still have the 8. The u is raise the power, u to the 3 halves, divide by that power, and evaluate at those endpoints. And so this answer isn't very nice, but it's pi over 4, it's 2 over 3, could have simplified that some more, and then it is the 37 to the 3 halves minus 1. One more simplification there if you really want. Since I always do it, I think it's pi over 6, and then 37 to the 3/2 minus 1. I don't think I can get any better than that. So why did I want to make sure I did this one? I wanted to show you guys, again, the weirdness of like projecting back down. When you're doing these surface integrals, you're working on this surface, but when you go to do the integration, you've taken care of the fact that it is a surface, and you only need to think about what space it actually takes up as a projection back to the xy plane. So I think that's always a little challenging. It's something I struggle with in these integrals, is because it doesn't, it's weird. You've already taken care of the fact that it's curved with this integrand, so all you're left with then is to just assume to project it back down onto a flat space. Remember, area integrals are just area, right? They're not volume. So you are on a flat space after you've done this integrand. Kind of weird that the integrand gives you all you need to figure out the surface area. All right, encourage you guys to practice this. Again, remember your dA. The dA did change to r dr d theta. Again, because in the xy plane, that's how it changes. We had that one with the polar coordinates where it didn't change, right? I didn't have to use the Jacobian there. But here, these were x's and y's, and then I made them r's and thetas. That's why I made that change there. That change was not in the r originally. We weren't in the very beginning r. Okay, hopefully I didn't confuse this too much. Hopefully you guys will do great here, and make sure you try your homework, okay? All right, I will be back on Wednesday, and we will use some of these surface integrals for some things like electromagnetism, because we're going to start talking about a vector field passing through a surface. All right, keep working hard.